Okay, so today we're going to be looking briefly at beta oxidation, and we're also going to be looking at the factors that control it. We're also going to be looking at the factors that inhibit it, and then we're going to be talking about the general function of and how it is incorporated into the general cellular metabolism. So the first thing that occurs with beta oxidation is knowing where it happens. So I'm just going to quickly sketch out a normal mammalian cell. Okay, and so within the mammalian cell there are various different organelles. So the one that we're interested in here is the mitochondrion. So I'm drawing the mitochondrion on. As we all know, there are various different areas within the mitochondria. The one that is the most significant for this is we need to know that there is an outer membrane and an inner membrane. The inner membrane is in folds in something that is known as cristae. Cristae, like I said, are folded up, so there is a high surface area to volume ratio, which means that there is a high exposure between the inner and the outer, or the inner matrix and the intramembrane space. So what needs to happen in beta oxidation is the breaking down of fats into acetyl-CoA, or specifically fatty acids. So let's draw some fatty acids in the cytoplasm of the cell. So obviously fatty acids, I'm just going to draw them on here, have an OH group on one end, and also, because obviously there are fats, they're going to have an oxygen group which has a double bond onto the carbon, and this forms the end bond. So medium and short chains can diffuse straight through into the matrix through the two layers, and this is by passive diffusion. So I'm just going to stencil that on here with a passive diffusion. However, if the chain is longer, so I'm just going to stencil it in down here, then it has to go through something called the carnitine shuttle. Now, the first thing that needs to happen is that the fatty acid will need to bind to something called CoA. Now, CoA is a large polar nucleotide derivative. So I'm just going to stencil that on here. I'm just going to put plus CoA. And this then allows it to be transported into the intermembranous space, because the outside membrane is leaky, the inner membrane is not leaky. So what needs to happen? The first thing that needs to happen is obviously the CoA, like I said, is a large polar nucleotide derivative, and if the inner membrane, which is shown here, is not leaky, then the large CoA, which is polar, cannot pass through it. So the fatty acid, which is at this point fatty acyl-CoA, will then need to dissociate from the CoA and then bind onto the fatty acyl carnitine. So it forms fatty acyl carnitine. So carnitine basically takes the place of the CoA. And that occurs here at the carnitine transporter. Then the carnitine, or the fatty acyl carnitine, then travels into the matrix, where then the fatty acyl-CoA is reformed and the carnitine is then removed. Then the carnitine translocase then removes carnitine from the matrix into the intermembranous space, and it is recirculated. And the fatty acyl-CoA is then able to undergo beta oxidation It's important to note that the malonyl-CoA is the inhibitor of the carnitine shuttle, and this is significant, and also we will cover the significance of this during fatty acid construction within the cell. So we've covered the carnitine shuttle and how fatty acids travel from the cytoplasm into the matrix, where then they're able to undergo beta oxidation, as shown here. Right. Now, let's talk about the actual mechanistic process of beta oxidation. Okay, first you will start with a chain of okay, I'll try and make that a little bit wider, just so it's more visible. So this is our fatty acid, okay? And these red things, these red dots, indicate the position of carbons within it. So the typical fatty acid will be well, palmitoyl, which is the main storage one, is 16 carbons long. But the first thing that needs to happen is that you need to appreciate what is happening at the end with the carboxylic acid group. So obviously it is stored as I think I use yellow. Okay, so R represents that this process goes on, and that travels off to the left. So traveling off to the left of the screen is the increasing length of the fatty acid. Okay, so here I'm now going to show this is at the carboxylic acid group to the right. So there's an arrow indicating the carboxylic acid group off to the right. And this carboxylic acid group is attached onto the CoA, and the CoA attaches on via a sulfur bond. So I'll stencil that in. Now the reason it's called beta oxidation is the point of cleavage is actually not the first carbon shown here. So that's number 1. It's number 2. It's actually at the second carbon. So obviously alpha corresponds with 1, beta corresponds with 2. So what happens? Now the first thing to occur is between the first carbon and the second carbon, and this is where a double bond is formed between the third and second. So here's the third one here, and here's the second one here. Now a double bond is formed, so I'll just stencil that in, which means that there is a loss of hydrogen of 2. So then we get formation of FAD2H. Because there is a loss of hydrogen from here and here to allow the formation of the double bond. And that's the first thing that happens. And this is carried out by, I'll just stencil this in. So, and this is the step 1 is caused by acyl-CoA dehydrogenase. So this is phase 1. Now we're going to be looking at phase 2. So we get rid of this. So at this point we have a double bond between 2 and 3. And now we are going to add H2O. And the adding of H2O is by an enzyme known as ENOYL-CoA hydroxylase. And that is, grab a yellow brush, that's the addition of H2O. And that breaks this double bond, and instead makes this one here, makes the beta carbon revert back to being normal, and it allows the third carbon to then have an OH group or hydroxyl group added to it. Which is good, because then it means that the it allows for the next step to happen. So the next step to happen is the conversion of this hydroxyl group to an aldehyde, or rather into a or it basically removes the hydrogen from here and the hydrogen from here and forms a double bond onto there. So this is the next step, and I'll stencil that in, and that is by hydroxy-CoA dehydrogenase. And then finally, because what we end up with is we end up with a so we end up with that. Then thiolase, which is the next enzyme in the process, and the final one allows the severing here between the second and the third, carbon in the fatty acid chain, and also the addition of S-CoA onto the third one. The consequence of this is that you end up with acetyl-CoA produced, which is this portion here, and also then you have a reduction by a length of 2 carbons of the fatty acid length, which is shown extending from the middle of the screen off to the left, and that is fatty acid beta oxidation.